Okay, now that we got the concept of power series down and the interval convergence, which again we think of like the domain of the power series, the next thing we want to start talking about is this concept of representing a function by a power series. So we've already considered power series as a function of x, right? But even more so, we can look at which function of x can be represented as a power series and what power series that would be. So the easiest way to get into this is to start talking about it in terms of geometric series. So let's look at this geometric series. F of x equals 1 over 1 minus x. That looks really close to what a geometric series would converge to. So you think about a geometric series, a r to the n. As long as the absolute value of r is less than 1, it's going to converge, and what it's going to converge to is a over 1 minus r. So if we think of this here as a and this as r, this does have the form of a over 1 minus r. So if a is 1 and r is x, 1 over 1 minus x should be what this series here, a being 1, r being x, which would give me the sum of n equals 0 to infinity of x to the n. That's what that should converge to, as long as the absolute value of r, in this case, the absolute value of x, is less than 1. Now remember, the absolute value of x is less than 1 is when this series will converge. And if you think about this, this is exactly what a power series should look like. And this is the interval of convergence, because you can write this also as -1 is less than x is less than 1. So these are the x's that we could use that would plug into here that would make this series converge. And this is what it would converge to. So what we just did is we said that this function, 1 over 1 minus x, which we've seen multiple times before, all throughout our algebra days up through calculus, with this function is represented by this power series, n equals 0 to infinity of x to the n. So ultimately, when we started series, there were two questions that we had to ask. One was, does the series converge or diverge? And two, if it does converge, what does it converge to? And that second question, we haven't really been answering all that well. We did a little bit, we did with geometric series, we did a little bit with approximations in alternating series, but ultimately, we haven't been answering that question very well. But we have been focusing more on, does the series converge? And so now power series, when we talked about interval convergence, it was which x values can we use that would make the power series converge? And again, we still didn't really say, well, what does it converge to? But now that we have this representation of a function and a power series, that this function and this power series are equal to each other, we can answer that second question. So if we use an x value between -1 and 1, okay, and I plug that x value in here, I know I'm going to create a convergent series. If I take that same x value and I plug it in here, I know what that series will converge to. So let's say x is a half. If x is a half, the series would be n equals 0 to infinity of 1/2 to the n. I know that's a convergent series because that x value came from this interval of convergence. I also know then that this series would converge to 1 over 1 minus a half. Now you might say, well, that's not a whole lot different than what we already knew through geometric series, but this is just the beginning of it. If we can continue to do this, if we can continue to find functions whose representation is done through a power series, we can continue to use this concept of, we have a series, we know which x values we can plug into that series that will make it converge, and we'll know what it converges to. This is just, again, the beginning of that concept. But representation of functions by power series is essentially the idea of how we answer that second question. Okay, what does the series converge to? All right, so here we want to find the power series expansion centered at 0 for this function. We're going to do this through geometric series, just like the last example. We have this function 4 over x plus 2. We want to write it as a power series centered at 0, so that would be a sub n x to the n. That would be a power series centered at 0. So we're looking to figure out what this power series would actually be. Really, we're ultimately trying to find this a sub n piece. So we need to write this in the form of a over 1 minus r, so that we can write it as a power series a r to the n. As long as the absolute value of r is less than 1, it's going to converge. So let's look at 4 over x plus 2. If I do a couple of things here, one, I'll write it as 4 over 2 plus x. Again, I'm trying to get it to here. So I need to make this a 1. In order to do that, if I divided it by 2, I could make this a 1, but I can't just divide that piece by 2. However, if I divide both the numerator and the denominator by 2, then I'm really multiplying the whole fraction by 1. I'm basically multiplying by a half over a half, which is 1. So this is legitimate. That would give me 2 over 1 plus x over 2. Then I got to get the minus r. So this has to turn into a minus. Well, if I do a double negative, that's the same thing as a plus. And now I could say that this is my r and this is my a. So I have a over 1 minus r. Well, if that's the case, then this should be written as the power series n equals 0 to infinity of a r to the n. Now to make this look a little bit more like that, I'm going to mess around with it. So I would have the sum of n equals 0 to infinity of 2 times negative 1 to the n, x to the n over 2 to the n. Essentially, I'm just going to raise everything in here to the nth power. So that means the negative, the x, and the 2. I can bring this 2 to the denominator. So I have the sum of n equals 0 to infinity of negative 1 to the n, x to the n over 2 to the n times 2 to the negative 1, which I can then write this as the sum of n equals 0 to infinity of negative 1 to the n, x to the n over 2 to the n minus 1. So now I did all that because this is my a sub n piece, and here I have x to the n. This is a power series centered at 0. And that's the power series expansion for 4 over x plus 2. But 4 over x plus 2 will only equal this power series if this power series will converge. Well, when will it converge? It'll converge when the absolute value of r is less than 1. What was r? R was negative x over 2. So as long as the absolute value of negative x over 2 is less than 1, it will converge. What I'm really doing here is finding the interval convergence, but I'm doing it through geometric series, not ratio or root test like we did previously, because we have this information. If I wanted to use ratio test on this, I could, but I have this information sitting in front of me through geometric series, so I'm going to use that instead. So anyway, I got to solve this inequality. The absolute value will get rid of that negative, so I have the absolute value of x over 2 is less than 1. Multiply the 2 to the other side, absolute value of x is less than 2. Get rid of the absolute value now by making a compound inequality, a double inequality. And there are the x's for which my series will converge. If I choose an x between negative 2 and 2, I plug it into this series. For x, I'm going to get a convergent series. If I take that same x value and I plug it in here, that's what the series will converge to. There are infinitely many different x's between negative 2 and 2. Infinitely many different ones. Choose any one. And I plug it into here, I know I'm going to create a convergent series. Plug that same x into here, I know I'm going to figure out what that series converges to. But I can only do it with these x's. If I choose any other x, this is not necessarily true. 4 over x plus 2 doesn't necessarily equal this power series, negative 1 to the n, x to the n over 2 to the n minus 1. This will only equal the power series if I use these x's right here. But there's infinitely many of them. So the benefit I get out of this is I don't have one series and I know what that one series converges to. I actually have infinitely many different series and what each one of them is going to converge to as long as I stick with these x's. Okay. Okay, for this one we want to find the power series expansion centered at 1 for f of x equals 1 over x. Again, we're going to try and do this through geometric series. It's not always something that's going to work. We're going to do it for this example, but eventually this is going to get exhausted and we're going to have to come up with something else. But nonetheless, we're going to look at geometric series. We have this 1 over x. We want to write this as a power series centered at 1, so that'd be a sub n x minus 1 to the n. That's what we want our power series to look like. Way we're going to do that is we're going to try and look at this as a geometric series in the form a over 1 minus r, and the geometric series would be a r to the n. Now if you kind of relate this and this together, we're going to need our r to look something like x minus 1, and we're going to have to make this look something like a over 1 minus r. So we got to mess around with the 1 over x. So I'm going to write this as 1 over 1 minus 1 plus x, in which case 1 minus 1 is 0, so this is still 1 over x. Then I'll write this as 1 over 1 plus x minus 1. Now that's going to get me the minus 1 for my r. Now I just need to get it into the 1 minus r. This is 1 plus r. So like we did before, we could do a double negative. 1 minus negative x minus 1. And so here, this whole piece is now going to be my r. This is my a. So we have a over 1 minus r, in which case that should be equal to the series n equals 0 to infinity of a r to the n. Now just a little bit of work here to get it completely into this form. If I raise this negative to the n and this x minus 1 to the n, I would get the sum of n equals 0 to infinity of negative 1 to the n x minus 1 to the n. And there's your power series. Okay, that's your power series centered at 1 for 1 over x. Now again, that's only going to exist if I stay in the power series interval of convergence. What is this power series interval of convergence? Well, remember, this will converge when the absolute value of r is less than 1. What was r? R was negative x minus 1. When the absolute value of that is less than 1, it will converge. Well, which x's will satisfy this inequality? Well, the absolute value can get rid of the negative, so I have the absolute value of x minus 1 is less than 1. Get rid of the absolute value by doing a double inequality. Add 1 to both sides. There's your interval of convergence. Those are the x's that I could plug into here that would make this a convergent series. And if I took those exact same x's and I plugged into here, that will tell me what the series will converge to. The interval from 0 to 2 has infinitely many different values in it, and I can choose any one of them. Okay, I don't know, let's say square root of 2. Okay, if I take the square root of 2 and I plug it in here, that's going to create a convergent series. And if I plug the square root of 2 into here, that's going to be what that specific convergent series converges to. And that's just one value that came out of this interval, but there's infinitely many x's between 0 and 2 that I could choose. So again, this example has given me infinitely many different series and what each one of those series will converge. That's the benefit of this idea of representing a function with a power series. So once we have a concept of a couple of different functions that we could represent by power series, we can then start thinking about using some operations to combine some of these series together or to alter some of the existing series. So here are 3 different operations we can work with. First, if we have one function that we can have a power series representation of, and we have another function we can represent as a power series, we can alter each one of those individually using these 2 operations. So what it says here is, let's look at the first one. It says if I have a function and I alter the function by multiplying by some constant k is a constant, okay, then I should alter the power series by an extra k to the n inside the power series. So what do we have? We have a function, and that function is 1 over 1 minus x, and we saw the power series for that is n equals 0 to infinity of x to the n. So then if I say, how about we find f of 3x, which would be 1 over 1 minus 3x. And I said, okay, well, there's a different function, but it's not completely different. It's related to this original one in that I did f of 3x instead of f of x. I just plugged 3x in for x. Well, the corresponding power series would essentially just have an extra 3 to the n inside of it. So I can build off of one to create another one. How about this? F of x to the n. So what if I said, what about f of x squared? Well, f of x squared for this function will be 1 over 1 minus x squared. But what would the corresponding power series look like? Well, the corresponding power series would need an extra power. This n, capital N, would have to be multiplied in the x to the n that was already there. So this would be the sum of n equals 0 to infinity. Originally was x to the n, so now it's going to be x to the 2n because of the square. So some of these operations can help us alter existing functions in power series, so we can build off of what we have already. We can also combine two of them together. So let's look at this one here. It says if I have two functions that I want to add together or subtract together, I can also add this corresponding series together. Now, there's a couple of things here that need to be said. One, in order to do this, both power series have to start at the exact same index. Either 0 or 1 or 2, it doesn't really matter, but they have to start at the exact same spot. And they both have to be centered at the exact same place. So if I look at, say, this example here, 1 over 1 minus x equals the sum of x to the n. And we had another one, let's say, what was it? It was 4 over x plus 2. And that was equal to the sum of n equals 0 to infinity of negative 1 to the n, x to the n over 2 to the n minus 1. If I look at that one, and let's say I wanted to do f of x plus g of x. Well, for the functions, that would be 1 over 1 minus x plus 4 over x plus 2. And I could add those two together. I could find a common denominator and put it all together as one fraction. But whatever that ends up being as one fraction, it should be equal to the sum of n equals 0 to infinity of x to the n plus the sum of n equals 0 to infinity of negative 1 to the n over 2 to the n minus 1 x to the n. And I can put these two series together as a single series because their index starts at the same spot and they are centered at the same thing. And all I simply have to do is add this corresponding coefficients. Well, in this case, the coefficient is a 1, and here this is the other coefficient. So the series that this should be equal to would be the sum of n equals 0 to infinity of 1 plus negative 1 to the n over 2 to the n minus 1 times x to the n. That's what this function's power series representation would look like. So again, this gives us the ability to alter existing functions in their corresponding power series. Okay, now this geometric series stuff only takes us so far. We have some of these properties of operations that we can do, but again, the a over 1 minus r, not every function has the form of a over 1 minus r. You know, 1 over x, we were able to eventually get into a over 1 minus r. But what if I said find the power series expansion for log x? Log x does not look like a over 1 minus r. So trying to come up with a power series centered at 1 for log x is not going to happen through this geometric series concept directly. However, we can use some of the things that we've talked about as it relates to power series to do this. We know that this function 1 over x is equal to this power series. Okay? So if that's the case, do you know there's a relationship between 1 over x and log x as functions? Well, yes, we know that one is the derivative of the other, or we can talk about integration, okay? Because it depends on which direction you want to go. So thinking about this, if I know that 1 over x equals the sum of n equals 0 to infinity of -1 to the n, x minus 1 to the n, and I also know that the integral of 1 over x dx equals log x, well then the integral of the sum of n equals 0 to infinity of -1 to the n, x minus 1 to the n should be what log x's series looks like, as long as I can integrate this power series. Well, we talked about how would you integrate a power series. Also differentiation, the same thing. So since this function equals this power series and the integral of this function equals log x, then the integral of this power series should be what the power series for log x is. So what's that going to be? Well, how do we integrate a power series? We have c plus the sum of n equals 0 to infinity of, use the power rule, -1 to the n. The x is raised to the n, so that's where our power rule is going to come in. We don't do anything with the -1 because that's just a constant. So we have -1 to the n plus 1 over n plus 1. Integration power rule. Add 1 to the power, divide by the new power. So there's your power series for log x. Now, what was the interval of convergence for this series? Well, the interval of convergence for this series was 0 to, let me get 3, I believe. Okay. So the interval of convergence for this series should also somehow be between 0 and 3. Now, do we include the endpoint or not include the endpoint? Remember, that's the only thing that can change with the integration. But as long as I choose an x somewhere in this interval, not at the ends, I know for sure that it will converge. So why am I talking about this? Well, I'm talking about this because we actually have the c here. And so this isn't actually the whole answer. If we can figure out what c is, then we have the exact power series that this log is equal to. Well, let me choose an x value from inside this interval of convergence. Not on the ends, because that would be questionable, but let's go inside. Let's choose 1 specifically. So if I choose, say, 1, log of 1, I don't know, is this what this was 2 or was it 3? I can't remember at this point, but it doesn't matter. I'm pretty sure now I'm thinking about it, it was 2. But anyway, if we go inside here, let's say 1. If I take the log of 1, I know the log of 1 is 0. If I also let x be 1 on this side, that's going to create 0 here. So every term of this series will be 0. So what I'm going to get is c plus 0 plus 0 plus 0 plus 0, etc. So I know all that's going to be 0. So then if you look at what happens, this tells us what c should equal. C should equal 0. So then I can do better than just log x equals c plus. I can do log x equals, get rid of the c because c is 0, the sum of n equals 0 to infinity of -1 to the n, x minus 1 to the n plus 1 over n plus 1. And I have a basis for what the interval of convergence for that would be. The only questionable part would be possibly the endpoints, but as long as I stay away from the endpoints of the interval, I have a bunch of x's inside that I know this is going to be true for. And if I wanted to additionally test the endpoints to figure out exact interval convergence, I could do that as well. But there is a power series for log x. Log x isn't directly an a over 1 minus r function, but it's related to an a over 1 minus r function through integration. So we can use derivatives and integrals to get us to the a over 1 minus r. That could then get us a particular power series. Okay, so here, same concept. We're going to try and find a power series for arctan. Now, arctan, again, is not a function that has the a over 1 minus r field to it. It's not. There's no way I'm going to get there directly. But I do know that the derivative of arctan is 1 over 1 plus x squared. Or I could also say the integral of 1 over 1 plus x squared dx equals arctan x. Now 1 over 1 plus x squared, that does have the a over 1 minus r field. So let's think about this. If I know that 1 over 1 plus x equals the sum of n equals 0 to infinity of negative 1 to the n, x to the n. I could also use my operations to say 1 over 1 plus x squared equals the sum of n equals 0 to infinity of negative 1 to the n, x to the 2n. Using the idea that this is, if this is f of x, then this one here would be f of x squared. So I need an extra 2 up in this power. That was one of the operations we talked about. Then knowing this, we could say, well, then the integral of 1 over 1 plus x squared dx should be equal to the integral of the sum of n equals 0 to infinity of negative 1 to the n, x to the 2n. And the integral of 1 over 1 plus x squared is arctan x. So the power series for arctan x should be whatever the integral of this series is. Well, that should be c plus the sum of n equals 0 to infinity of negative 1 to the n, x to the 2n plus 1 over 2n plus 1. Again, add 1 to the exponent and then divide by that new exponent. That's how you integrate using power rule. So here is your power series for arctan. Now we have the c sitting here, which is just some random constant. If we could figure out what that constant is, then we could come up with the exact power series for arctan. Now remember, as long as we stay inside the interval convergence, this function will equal this. Well, you're always guaranteed to be inside the interval of convergence as long as you choose the center. The center of this power series is 0. So if I let x be 0, I know for sure that this power series will converge and this equality will hold. Well, arctan of 0 should be equal to c plus the sum of n equals 0 to infinity of negative 1 to the n, 0 to the 2n plus 1 over 2n plus 1. Well, what's this going to be? If it's 0, every term is 0, so this whole thing is 0. So this is just saying arctan of 0 equals c. Arctan of 0 is 0, so c equals 0 again. It's not always going to happen that way, that c is going to be 0, but in these two examples it did. So finally, arctan of x has the power series n equals 0 to infinity of negative 1 to the n, x to the 2n plus 1 over 2n plus 1. That is the power series for arctan. Again, arctan doesn't have the a over 1 minus r field, but it sure is related to a function that has an a over 1 minus r field. So Again, we can somehow get back to a over 1 minus r. If there's any way to get your function to somehow get back to a over 1 minus r, then we can use this geometric series concept to get to a power series representation.